I'm going to see if I can get this pulled up so that I can see what the comments and stuff are that are coming in. There's no audio. Okay, sound's on now. Zach Zeller, my buddy who lives down the street, is watching. All right. Man, get back to work, dude. You never do anything. Still, hey, man, I wanted to ride on the little pink four-wheeler yesterday. Audio's up now. Okay. You're good?
Good.
I'm good. Bill's good. All right, let's get back into the questions. We had just covered how passionate Bill was about wellbore tortuosity. Bill, recap that one, and then we'll go from there.
Yeah, I mean, I got hooked on directional drilling and number crunching with directional drilling 40 years ago, doing surveying. And then I was a wireline engineer away from directional drilling. I'd come back and I would crunch that kind of data. And then I'd go do something else. And I came back and I started doing horizontal wells, and then went to work in casing drilling of all things, a bunch of different things. All the threads are new technology, and all along the way, there were new developments in directional drilling. Surveys remained the same, and tortuosity and associated computations with placement had changes each time. Technology changes in the variations that happened in horizontal wells. I was working horizontal well projects and extended reach wells. We could talk about extended reach stuff if you want to, and that. And anyway, now there's these thing called unconventionals, and I'm trying to see what's going on a technical side with those wells, and tortuosity is my major tool for doing that.
So, in your experience of doing all of these different things, what has impacted the industry the most that you think, as far as, let's say, new technology wise? Because
wow, yeah.
I mean, being on wireline, being on drilling, being casing drilling, obviously it's a lot of the upstream side of it. What one piece of technology stood out the most to you?
Well, I mean, that pretty much has to be horizontal drilling. Before, I mean, this is going way back. I mean, horizontal kind of came into its own right around 1990. I mean, that's 30 years ago now. And it's gone through a lot of different variations. But the industry is completely different now with the application of horizontal. Now, then there's been lots of different flavors of horizontal.
Yeah.
The original Bakken that happened in 1990 led to a bunch of different horizontal projects international. And it took about 15 years or so for horizontals to take off in North America, basically, if you will. And then the variation of, well, let's put a horizontal down there and see how many natural fractures we can hit. That was interesting. And then let's put a horizontal down there and hydraulically fracture it ourselves and make a whole bunch of fractures, which is currently what's doing. So right there's 3 different steps in horizontal operations that have changed the industry quite a bit from my point of view.
Excellent. All right, so let's get into the meat of it for today. I know this is what you're extremely passionate about. For myself, as well as the people watching right now, give me a definition of wellbore tortuosity and what it is that, as we dive into this conversation, because we're definitely going down this rabbit hole today.
Yeah.
What do we need to know first before we even, jump too far off into the weeds?
Tortuosity has kind of a screwy definition if you look it up. It says the measurement of something tortuous. Doesn't really help. But an osity means measurement of something. Yep. So like viscosity is the measure of something viscous. Okay, so remember that osity is a measurement. Now, what is tortuous? That is having bendings, windings, and curvature, basically. So that's the official definition of tortuosity. And there's tortuosity all over the place. There's tortuosity in the upstream and the downstream oil field. Bending, winding of pipes in refineries. They do tortuosity. Tortuosity of the veins in the human body. And I bring that one up because a lot of people have borrowed this tortuosity measurement that the medical profession does, and that's what they've done up in Austin, far away Austin, where they have good internet. Dr. Van Oort and his group have taken this medical tortuosity index and augmented it for the oil field to use the metrics for. There's something that was measuring the health of veins in your eye.
I saw that on the eye.
Yeah.
Wearing my IADD board of directors shirt today. If you go to the one that he's referencing, and sorry to interrupt, but like if you want to see what he's talking about, there is a download on the IADD website, prior events, or its documentations. I can't remember exactly where it's at on the website, but there is a download on there about what you're talking about. So I'll let you go ahead and finish. Just so anybody else, if you want to reference it while he's talking about it, that's where it's at. It's on the IADD website.
And in trying to define tortuosity, bringing out this veins in your eye medical tortuosity, that's kind of where the argument is right now, because a lot of people are investigating that quite substantially. It's an indice that's been out there in a completely different profession, so it's bringing some new light onto it. But the measurement of something tortuous, getting back to that, sounds really simple, but the problem we have in the upstream oil industry is that, according to another friend of mine, there are 18 different definitions of tortuosity that just the drilling industry or the well construction industry, if you want to call it that, is currently using. And I've been involved in 2 previous iterations of looking at tortuosity, like I was saying earlier, coming back to directional drilling or horizontal wells and whatnot. So it's really kind of confusing right now. And one other thing I'd like to say is that the ISQA, the Industry Steering Committee on Wellbore Survey Accuracy.
Industry Standards Committee for Wellbore Survey Accuracy, a subsection of the SPE or subpart of wellbore.
Yeah. Tell me what it's called in the SPE, because that's even worse than ISQA.
Wellbore positioning or wellbore
positioning
technical section. Wellbore. I'm going to the meeting in Calgary. It's like,
and it's really something when ISQA is easier to say than that. Okay, and that's that. But anyway, there's a meeting after the SP annual convention in Calgary.
So it'll be October 3rd this year in Calgary.
Yeah. Mm-hmm.
It's just after the SPE ATCE event.
Right.
For anybody that's interested. So,
and
I'll be there.
That happens twice a year. They about a half a year later, after the annual big drilling conference. Now there's a lot of drilling conferences, but the one that's in end of February, beginning of March, the ISQA meets after that, or the SPE subsection, whatever it's called, meets after that. Anyway, the people, the workers, the technical investigators that are looking at this, that have been doing it quite a while, are getting ready to review tortuosity and try to get to some kind of understanding what all the definitions are. Okay, now I like the KISS principle. Keep it simple, stupid. And so in light of all of that, I concentrate on what's called large survey tortuosity. Teresa Baumgartner wrote a really nice paper, and she's is with Shale, formerly a student at Varick, and presented a paper at the drilling conference, the previous drilling conference, the one that was in the Netherlands this year, kind of detailed all of the major tortuosities. So if anybody wants to look at where we are currently with definitions, it's in Teresa's paper. And I like what she called large tortuosity. And large tortuosity is truly simple. You take the curvature between each survey, which is currently calculated as dogleg severity. There's 3.5 degrees per 100-foot curvature between 2 surveys that are 90 feet apart. So the actual curvature is 90 feet times 3.5, so it's 3.2 or something like that. So there's a curvature that you can calculate straight away from surveys as it's reported right now. And you add up all of that curvature, and then you divide it by the length that you're measuring, and you get something that is in degrees per 100 foot, something you can understand. If a 10,000 foot lateral has 200 degrees of curvature, that means it has 2 degrees per 100 foot tortuosity. Now, the problem with large is it sounds real similar to dogleg severity. It's not dogleg severity. You can't just average all the doglegs and get tortuosity. If all the surveys were equally spaced, you could probably do it. It's fairly similar to it. But the bottom line is that if I say this lateral has 1.5 degrees per 100 foot tortuosity, and this other lateral has 3 degrees per 100 foot tortuosity, you get a feel for the kind of curvature that's in each of those wells. So whereas some of the other tortuosity indices, if you will, and what's called the UT tortuosity index, UTTI, that's this eyeball thing, if I could call it that. I shouldn't call it that, but you get a feel for it.
The veins in your eyeball.
And that's what they based it upon. That's a dimensionless variable. You know, it's more or less of a ratio, so it's an indice, so it has a value. And interestingly enough, the current work that the different people at the University of Texas in Austin and A&M, and I don't know if the Aggies and the Longhorns are working together or not. You know, I think they are. But then also at the Colorado School of Mines, different people are working on these tortuosities, and now that tortuosity index has morphed into 4 different tortuosities. So there's the Shale version, the Hess version, the Apache version, and I think it's the Pioneer version. Okay. Now, and this points out why there's a lot of different tortuosities. There's different tortuosities because different investigators are looking at different things with the computation or the analysis of tortuosity that they're doing. And that's kind of what's happening with the 4-operator approach that they're doing with tortuosity. And I do the same thing. Large tortuosity is actually insufficient for what I'm trying to do. So I'm even, if you will, disagreeing with myself. I have different, okay, large isn't going to help me with this particular problem. I want to know about undulations, big undulations in laterals that may cause sumps that would impact productivity. Well, tortuosity doesn't handle that really well. You can have a well that has real low, large tortuosity, and it has nice big undulations that would kill off productivity. And you can have a lot of tortuosity, and the well is relatively smooth in terms of undulations. So this is why there is so many definitions, and why the various workers in the ISQA is going to have to thread the needle carefully, and there's not going to be one final tortuosity. What there's going to be is saying, if you're investigating productivity, here's the recommended tools that you could use. And if you're investigating placement, here's another set of tools. It's probably going to...
And like another one for torque and drag, or...
And then there's the whole, the torque and drag thing, which I'm kind of holding my thunder on that one.
All right, guys, if you're enjoying the show so far, be sure to comment, hit the little buttons down at the bottom, let us know that people are actually watching versus just seeing the number on here. It says there's 32-something people watching right now, but we want to see you guys interacting. Be sure to throw out some questions. Let us know what you like. Also, please share. Let other people experience some of the knowledge that's being shared by Bill on the show today. So let me ask you this. So we covered a little bit there about what is tortuosity, the measurement. There's multiple different measurements. What are some of the things that operators, because that's where, I should say operators and service companies, why should they start to look at wellbore tortuosity? Why should they start to be able to say, okay, hey, look, maybe getting a person involved, having you come in and consult, or just slowing down their day and saying, hey, we should start looking at these things? So we've talked about the measurement. What's the reason why they need to start to look at this measurement?
Okay. Well, again, what era are we in? Because if you were saying, okay, we're doing extended reach wells, which I know you've been looking at more than I have been recently, you would have reasons you were looking at for tortuosity with extended reach wells. We're in unconventional wells. I hope everybody wants to talk about unconventional wells, because that's what I want to talk about.
Yeah, no.
Okay, so now in these unconventional shale wells that we're doing massive hydraulic fracturings on, they're massive hydraulic frac jobs on, I guess is the way I'd say it. There are really, four major reasons you would want to look at tortuosity. First one is the one that's kind of been around for a long time. If you have a more tortuous well, you're going to have more side force. This is the torque and drag thing. The best way to say it is you're putting energy into destroying rock. You want the energy at the bit. You don't want the energy eating up on the tools and everything. Tortuosity causes tool failures. Tortuosity causes dynamic problems, leads to whirl and things of that nature. There's the whole list of drilling mechanics issues, and most people, including me, can make an argument that you can start a well off very fast and drill really fast and get high tortuosity, and if you will, be ahead of the curve. But then, especially when you're going out on long reaches, on laterals and whatnot, you're going to start paying the piper. You're going to have trouble transmitting weight down to the bottom. You're going to start to have tool failures. Several people have said, that they can relate tortuosity to tool failures and whatnot. So that's a classic drilling mechanics reason. The second reason is setting that casing. In unconventional wells, we set casing, and then we perforate it. And then we're going to do this frac job on it where we have to have several thousand PSI of integrity. Well, you want the well to be very smooth so that you have a nice cement sheath around it, so that when you do your perforations and then you do the packers and you start pumping a frac, that it's going to go where you want it to go. If you have tortuosity, the casing will be up against the side on part of the well. There won't be any cement there. The cement will have crescent around it. You're not going to have pressure integrity. When you perf it and go to frac it, who knows where the frac is going to go? And that is kind of a dirty little secret. A lot of people don't really look at that. But it is probably one of the most important things in terms of constructing a well for a hydraulic fracture. The casing may be, think about it. We're going to run this casing in the hole. We might have to beat it in there if we have a lot of tortuosity. We're going to rotate it. We're going to put it under stress. Then we're going to shoot 2,000 holes in it. And the stuff may fail. It may part. Another associate of mine is a consultant for some of the premium connection companies, because people are calling him and saying, why is my casing failure? Why is my casing failing? Well, you crammed it in the hole, you rotated it, you shot 2,000 holes in it, you thermally stressed it a bunch when you did the cement job, and now you're pounding on it with multiple surges of 2,000 or 3,000 PSI when you do a hydraulic frac. It can only take so much. Well, if it's smoother and you have a better cement sheath in there, then you eliminate a lot of these problems. What is the final hook load when you set that casing? When did you have to rotate? Operators ought to be looking at that and saying, okay, well, how much tortuosity did I have, and how rough is it going to be in terms of the casing? And here's the big problem there. You can set the casing. We can go in and we normally just run in casing. At some point in time, we may need to rotate the casing when we're setting it, but we can go to rotating the casing and it will go all the way to bottom. And whew, we got the casing to bottom. It's really, there's no problem really doing that. The problem is what shape is the casing in at bottom? And actually it may even be in good shape, but you may not have pressure integrity with the cement job. And of course, drilling has handed that off to completion. So there's a kind of a demarcation point. So we may have caused ourselves a problem in the actual drilling and setting of casing. Is setting casing part of completion or part of drilling? I don't know. But certainly cementing or certainly perforating and pressure integrity is part of the completion. So I have an example of the best well in my study where the tortuosity is 0.6 degrees per 100 foot. And it's a long one, like 15,000 feet. It's one of the long ones in our soon-to-be like extended reach database set.
Yeah.
And right next to it, there's another well that has 2.4 degrees per 100 foot. Graphically, one is nice and smooth, and the other one looks like the stock market, Dow Jones Industrial Average. And and I say, look, here's this well that has less than 1 tortuosity. Here's the one that has next to 2. Every time I talk about it, a drilling engineer would say, I bet we could run casing to bottom in both of these wells. And I bet that one with the rougher tortuosity was drilled 2 days faster. And I love it when they say that because he's exactly right. But, what happened after that? You handed that turkey off to the poor completion guys and they got to figure out, what kind of cement integrity they have. Spent a lot of time on number 2 because that is a special one. Now, the third area is in production. And the idea being that a more tortuous lateral, if you will have these sumps in it. People have talked about this. And a lot of people are investigating the relationship between tortuosity and lateral and how well the well produces. And in fact, going back to Teresa's paper at the drilling conference, she did a very thorough statistical analysis of it and found really no correlation between tortuosity and production within the individual well. I have some issues with that, and I think they were too blind statistically. And they were looking at similar wells but from different leases, and there are so many variations from different leases that one well may look like another well on a different lease, but the rock is different, and you cloud the results in tortuosity. So what I have done is I like to take a look at the bigger Permian leases. I like the Permian because of all the other places, it's the most consistent. Things remain relatively consistent across a large range. Now, the geologists out there are going to raise hell because it's not consistent, but it's a lot more consistent than the Eagle Ford. So, if I can find a 2,000 or 3,000 acre lease where they've drilled 20 or 30 wells, and there's a wide range of tortuosity, it's all in a similar rock, if you will. Geologist is not in the same rock, and I know the rock varies. But there's a good range of tortuosity, and there's probably a good range in productivity. Most states require, and you and I look at the state data quite a lot, they do a 24-hour productivity test of a new well. So again, things are fairly consistent there. And what I've found is that in these wells that have, if you will, the data fidelity to where there's a range of tortuosity and there's a range of productivity, that you see with about a 0.5 correlation coefficient that tortuosity and productivity are inverse related, i.e. higher tortuosity, the lower production. And that's actually pretty good. There's about 30 leases in the Permian that are big enough for this type of analysis. So anyway, lots of people, that's the most popular one. People want to know if tortuosity is causing a loss in production within the individual well. It's an effect, it's not really big, but that's the one that's currently being studied most. I would almost say let's study the casing integrity one, because I think that impacts our wells more than anything else. Long-winded, I know I'm getting that long. Okay, the fourth area is in placement. Okay, there is not a relationship between tortuosity and placement per se, but the wells that have a higher tortuosity are going to move around, wobble, if you will, in the lateral. Now, wells are not drilled in isolation. We're talking 25 wells on a 2,500 acre lease, 8 wells on an 800 acre lease. You know, maybe there's a well for every 100 acres of the lease, if you will, roughly speaking. So that means there's a well that's up to the left of you, to the right, up and down, that's 400 or 600 or 200 feet away. You're going to frack it, you know, and a frack is something that what I call a default fracture is 400 feet high and 600 feet wide, an ellipse. Okay, now you put the well somewhere in relation to its neighbors, and you kind of don't want your fractures to intersect. It's called a frack hit. Now, if you have some wobble in there, you know, how significant is that wobble? If a well that has 2 degrees per 100 foot tortuosity walks 100 feet to the left or right, then that well is off from where you want it by 100 feet. And it's maybe colliding with the fracture in a nearby well. Yep. Kind of like we used to say there was a technical collision with 2 wells in terms of directional drilling. Now, if we estimate the fracture of one well to be a certain size, you know, and the well of another well to be a certain size, but the 2 wells have wobbled towards each other, and that fracture ellipse, if you will, or whatever shape it is, it doesn't matter. If they touch, that's a technical frack hit, basically. And not a lot of people are actually looking at that. You know, a lot of completion engineers, and if there are any of these listening, you know, oh no, we look at that.
If you're a completions guy, let us know.
So I mean, and the ones I've talked to, I said, what they're doing now in frack hits, they're saying, okay, what's the rock strength, you know, from the well we're drilling to the nearby well, and if the rock strength is changing, then we're more likely to have a frack hit. And I say, okay, well, I can understand between where the 2 fractures are, you want to know the strength of the rock between those 2. Wouldn't you want to know exactly if they're, you know, how far away they are? You know, are you just assuming it's a straight line? What kind of navigation are you doing to calculate where those perforations are in one well and where they are to the closest set of perforations in another well? And are you looking at the wobble that's going on? Oh yes, we do that. And the way it's kind of dismissed, you know, after years of hearing that kind of stuff, I'm starting to think, okay, do you really do that or not? I don't know. So those are the 4 reasons that operators should look at tortuosity. And the problem is it goes from all the way through drilling and cementing all the way through fracking. You should be looking at what is going on with the tortuosity in a well in relation to how it's placed, because it can impact the fractures. You know, are there many completion engineers that are designing frac jobs that are actually looking at the tortuosity and or the placement, however you want to calculate it? Yeah. Do we even calculate a index through a lease? You know, we talk in terms of the individual well and the measured depth of the well and the TVD northing and the easting of that individual well. We really don't relate a depth of lease, if you will, to say, okay, we are 1,200 feet into the lease with well A, and the closest approach is 1,220 feet on well B. And some people do something called a ladder plot. And there's various ladder plots, but the ones I've seen are kind of one-dimensional. They don't really address the 3-dimensional aspect of this placement problem. And I think that this placement problem, number 4, is a potentially big issue, as I don't think we're getting the fractures that we think we're getting. And then going to number 2, where are we even making the fracture to where we want to make it, or are we channeling somewhere else, or are we short-circuiting our fractures? And those 2 are not in the drilling domain. where we're actually constructing a well. We got the casing down and we're happy. So
that's always funny to me because, like, you know, if I've talked to somebody, they're like, well, you know, it doesn't matter. We can get casing to bottom. And it's like, if casing gets to bottom, it's like you have started a new blank canvas. It's like all problems have gone away once you say that you've got casing to bottom. But obviously, I mean, just in logical thinking, you can't think, oh, because I got casing to bottom, like all my problems are gone away. You know, if there were key seating or high sides, you know, those ridges, now it's been flattened out. You know, the casing's there, we shouldn't have any more issues. And it's like anything that drilling might have done prior to that, like all their sins have been washed away kind of thing. And it's like, if you take that approach, then you're ignoring the fact that, like, if you have issues in the future, that if you're trying to solve them, you're thinking of everything post casing to bottom. And you're thinking, okay, what is it among these things, as opposed to thinking there's a whole nother area that could be to blame. You know, I always tell people, like, when strange things happens, it's for strange reasons. And it's like everything's going fine, then all of a sudden something fails, and it's like, well, maybe you need to broaden your scope as far as, you know, what may have caused these issues. So I'm glad to be able to hear that. So I have to do this real quick. I've actually got a lot of good questions coming in, so we might have to do these in a lightning mode because I've already got
sure.
4 or 5 kind of racked up here. So thank you guys for watching. Please let us know where you guys are watching from. Please share. We're already up to 40 viewers in real time right now. Let's see if we can hit the 60 mark for today, guys. All right. So Mark Anderson says, he says, there is a question in my text. So let me go to my text messages real quick. Okay. So he says, question for Bill. What is the one unit? And he says, Bill gets to pick his favorite metric of tortuosity worth in terms of extra drilling costs.
Well, I mean, in terms of just straight drilling, I relate tortuosity to torque, and torque is energy wasted. That's kind of where I'm going with that. You got something to add?
He says, the point of my question is, until there is a dollar amount on tortuosity, then drillers can't optimize. Please give us drillers, because he's a drilling engineer, or
right.
a former drilling engineer. He still can be. Please give us drillers an NPV for lost production and extra well maintenance so we can optimize.
Well, thank you, Mark, for giving me an out there, because, I mean, in terms of drilling, I equate, and I've gone back and forth between curvature and torque. And if I wanted to relate what tortuosity was costing me, I would relate it to excess torque. Again, the torque and drag approach, because and really the only argument you could make out of tortuosity area number one is the problems that it's going to cause you in terms of potential tool failures. You know, statistically, you have more tool failures, and you really need to relate tortuosity to the torque that you're going to use in a well. And you know, if you should be able to drill this well with 14,000 foot-pounds of torque in the ideal case, and you're using 24,000, then you're burning up a lot of excess energy that's just destroying iron and slowing you down. You know, that's that argument. To get, and I'll for sanity's sake, I'll just concentrate on the unconventional laterals, because there's different arguments for tortuosity in the build section and in the vertical in the nudge section, and lots of different workers are addressing these things. But we
actually have a question about that.
Yeah, you probably would, because these are all the standard, the usual suspects that are being rounded up. The real problem is that almost everything I'm talking about here, the big issues are on the completion side. And you know, what I pray for is the drillers to let me have an extra day in the lateral and cut the tortuosity by 75%. And they don't want to do that because Mark is totally right. They are judged by the cost of their drilling segment in this process. And figuring out the cost of drilling in a net present value calculation is real easy to do. Figuring out the value of a project in terms of the overall well, the additional productivity that you get, or the better placement of your hydraulic fractures in a multi-well lease is real difficult to do. And in fact, we don't even talk in that language. And so, you know, I will fall for Mark's trap and say, you got me, okay? I can't get lower tortuosity and reduce drilling costs. Just can't do it. People want me to make the number one argument. Tell me how many tool failures I'm going to save on that. And you know, as my father says, there are lies, damnable lies in statistics. And I can work the statistics that say that you will pay less for your tool failures with lower tortuosity. But I could take the same data and make the other argument. You know, whoever would pay me the most, I would make that argument. Yeah. That's the way political consultants work. You know, the compromise that we get is kind of what Pioneer does. And Pioneer does an average job in terms of tortuosity. What Pioneer says is that I don't want to see a dog. We don't want to see a dog leg above 2 degrees per 100 foot. Okay. What that means is the directional driller is going to have to explain a dog leg that's over 2 degrees per 100 foot in the lateral. Okay, which they should actually. And what that means is he's going to back off the weight a little bit. He's going to keep the dog legs, or he's going to mess with the surveys. He's going to figure out a way to not show too many 2.0 plus degrees per 100 foot dog legs in the lateral. But you know, it will slow down the process. I mean, if you wanna drill the fastest way you can and get the casing down, then by all means, kick it and have a 3.0 degree per 100 foot tortuosity. You know, the numbers will work out. So yeah, you got me. Next question.
All right.
I'm 0 for 1.
All right. So next one. This is Kazim, who's a directional driller for BHDC. So we've got somebody watching internationally here.
Wow.
How can we optimize drilling speed versus tortuosity? By the way, is there any compromise for tortuosity to increase drilling speed? So kind of right where we were at with that previous question.
Well, you know, I mean, time or money, unfortunately. One of the biggest problems in, again, unconventional lateral tortuosity is you need a big old bend in the motor, and you got to do it with the motor to do the build, okay? And you severely want to keep going, especially on, you know, shorter laterals like 5,000 footers. You want to keep going with that same motor. Of course, that 1.83 band is going to really cause larger tortuosity, basically. But you can use it and you can get to bottom. Your slides are shorter, and of course you can set casing. Okay, so one of the you know, the best thing you could do is actually, you know, change the motor for the lateral, especially on 10,000 foot laterals, which almost everybody does nowadays. Or of course you can go to a rotary steerable system, which is, from a mechanics and technical point of view, the thing you should do. Of course, you know, I want you to have another trip. I want you to pick up an expensive rotary steerable system. I want you to slow down. I mean, the drillers are going to hate this stuff. I mean, it's just no other way around it, basically. And remember, everybody, that
doing things right is not about making friends.
Yeah, exactly. But what the end result is, you're going to get the casing down. What was beautiful was, before we could rotate casing, or before we had rotary steerable systems, drillers genuinely had to not have tortuosity. The early days of geosteering was that crazy geologist wanted to put a kink in the well, and the driller would say, okay, if you put a kink in the well, then you're going to shave off 500 feet in our lateral, because we're not going to be able to steer or get the casing down because we can't rotate. because we have a high sliding friction factor as opposed to a low rotating friction factor. I mean, you can bounce around between torque and drag and tortuosity and drilling mechanics and all these people that are out there baiting me on this one, and I knew this is what would happen. And thank you, I love it. It's a good argument. You know, they know these arguments basically, but the evangelical bend that I'm on right now is that drilling. Let's call ourselves well construction people. Okay, our objective is ultimately to get production. You've heard that be said before. Okay, well, production in this case comes from hydraulic fractures. Okay, you know, 5 nanodarcies does not produce unless you have major surface area in a hydraulic fracture. Getting the biggest and the best hydraulic fractures is what we should want to do. And these 4 elements of tortuosity to different levels affect what kind of hydraulic fracture we're getting. Okay? If we had a metric, and guess what? We do have metrics that could relate how we're drilling to what kind of fracture area that we're getting. And if you buy that fracture area is directly related to production, then we're starting to get to where, as well constructors, we should be thinking.
Yeah.
Now, I want to keep the well as cheap as I possibly can. Does everything I'm talking about make anything cheaper? You know, only if I lie. Okay, and I know how to lie too. So I when I get run out of the oil field, I'll be a political consultant. But anyway.
All right. So next question: what are Bill's thoughts on back calculating open hole friction factors from torque and drag to quantify micro-tortuosity? See previous work published by Blaine Como, so we know Blaine,
yeah,
and David Chin.
Oh yeah, okay, so I mean, I couldn't get into all the different flavors of tortuosity, but there's the eye tortuosity, there's large tortuosity, and then there's, I said large survey tortuosity. How about small survey tortuosity? This is the micro-tortuosity argument, and this is what Blaine and Wilson and a crusty old Scot named Tom Gaynor worked on. And really, this whole, and that's the spacing argument. As you might guess, if I had 90-foot surveys and I come up with 2 degrees per 100-foot tortuosity, if I went to 30, it's going to be 3 for the same well. If I go micro, it's going to be 5. Okay, the more warts and wrinkles come out, the closer you look at things. And all of the spiraling and the washboarding and all these cute terms that various people have heard about, they come out. Now, a friction factor, friction factors aren't really affected by survey spacing the way tortuosity is. So you can look at a well that has 2 degrees per 100-foot tortuosity, and it's going to have 18,000 foot-pounds of torque. And I talk in terms of torque as opposed to individual friction factors. You take the friction factor and you calculate the torque. But I like torque because I can relate to what that says. So, one well has 18 and the other one has 22, and they both the same length, both the same mud weight, all the same other stuff. And one has higher torque. That's because there's micro doglegs in there that you're not picking up on a 90-foot survey. If you went to closer foot surveys, you'd see all that stuff.
Yeah.
So and again, we're kind of lying to ourselves by surveying at 90 feet in laterals. We don't want to know what's down there. Okay, especially with those big bad motors. If you're drilling a lateral with 1.83, you do not want to know what that lateral looks like closer than 90 foot. Okay, because it looks bad. And anybody that's taken a look at, and nearly every MWD tool out there, and some don't, so don't tell me the ones that don't, but most of the MWD tools measure what's called continuous DNI, continuous inclination and azimuth. They're taking one of the accelerometers and they're measuring it like a gamma ray in a standard MWD stream, and one of the magnetometers. Now, maybe it's not as accurate as the actual survey, and there's a whole argument about that. But you could tell where we snuck in the slide and have really introduced a truly bad dogleg. And you could do, with a big motor, you could do a 10-foot slide and still come in with less than a 2 degree per 100-foot survey, tortuosity between two surveys, and you have a 13-degree dogleg, which is going to pinch that pipe up against something, and you'd never know it on a 90-foot survey. I mean, I'm talking about seeing 2-degree doglegs on 90-foot surveys. I would speculate that there's a pretty good chance that if it's over a 2-degree dogleg, that you're up against the wall, redneck, if you're in that kind of survey. Yeah. I don't even track 2-degree surveys. I track 4-degree surveys, and I count them per well because I count too many 2-degree surveys. And I would speculate that your casing integrity is suspect if you have a 4-degree dogleg between two 90-foot surveys.
I would say part of that good SPE paper that Ed Stockhausen wrote about, as far as surveying 90-foot intervals.
Well, I'm a co-author on those papers.
Oh, you go out. Oh, yeah. I didn't know. I didn't know. I just know everybody calls it the Stockhausen effect. So maybe it should be the Stockhausen Lesso effect. Well, as far as the paper that he wrote.
Yeah.
But
Ed clarified that, by the way, very graciously, because Ed, as everybody knows, Ed is crazy. And I hope you're out there watching it, Ed. I'm telling the world that you're crazy, but he's crazy like a fox. He's a crazy genius. I have tons of respect for him and everything. And it's called the Stockhausen effect because he is the one that makes sense out of it in terms of how it impacts production and how it relates to money. And specifically, the Stockhausen effect is this long survey spacing. When we have 90-foot surveys, we assume that the curvature is constant or uniform between two surveys.
Yep.
Well, if we put a slide in there where it's curving at 10 degrees per 100 foot, and then we're rotating at 2 degrees per 100 foot in whatever direction, the constant curvature assumption is invalid.
Yep.
Now, in actual survey computation, that means that the XYZ, TVD, northing, and easting is off, okay?
Yep.
And if you took the continuous surveys, or you had surveys that had constant curvature between them, you would calculate where the well is, at least for constant curvature, and it will be different from what it is with 90 feet. That's the Stockhausen effect. So Ed, being a geologist and on placement and in sand shale sequences that have water contacts, he basically said, for every foot we're off in some place in Africa, it's costing my company $1 million. And that is the Stockhausen effect. Now, Ed can't really crunch numbers very good, so I'm his number cruncher for him. So, I did the number crunching, for him on these things. Some people say I empowered him and made him more dangerous, effective, wild than other. I hope I did, because Ed has so impacted the geosteering world and how we understand laterals from a geological point of view, and helped drillers, and I'm quasi-drilling person, to understand the geological considerations. We've had many fights. We have to have mediators when we're writing SPE papers. That kind of thing. But the Stockhausen effect, to kind of summarize, says that there's something that's invalid when we have surveys spaced too far apart.
Yep.
Now, Ed worries about placement, and I'm currently worried about placement. Remember, placement's number 4 on my list.
Yes.
I used to worry about drilling mechanics. If you have 90-foot surveys, you're really not going to know where you have casing problems. You're not going to know about that one case that I'm talking about to where you don't have a uniform cement sheath. I think we need more uniform cement sheaths in these multilaterals, especially as we start putting these fractures closer and closer together. Right. So all of these things are related. Going way back to the question, which probably nobody remembers, but Talking about going backwards and forward modeling with torque and drag and friction between tortuosity is all valid. Again, the point I want to make is that torque or friction factors, if you will, are not susceptible to this survey spacing argument, where our surveys and our tortuosity is, and those that are using those techniques have a tool to deal with survey spacing issues. And our friends at Drill Scan are very good at this. Stefan and the crew there, they look at well bores, and in fact, they can almost reconstruct. They probably can reconstruct. I shouldn't be speaking for them, but they can actually reconstruct what's going on between 90-foot surveys based upon what they see in torque and drag analysis and whatnot.
Wow.
So it's a very helpful tool, and that's why I'm bouncing back and forth.
That's why that's also probably why they got purchased.
Yeah, there's some evil genius going on there.
Yeah.
Yes.
All right. So next question. Can you find, and this is from Mark LaRue, he's a sales manager over at Key Drill. So Mark, thank you for watching, sir. Can you find any relationship between planned back builds in the vertical section and the additional tortuosity in the lateral?
Oh, wow. Thank you very much. Okay. These...
excellent question.
These planned back builds, which, I would call S-shaped nudges, basically. How we got 3 wells on a pad, and we're going to nudge out in one direction for the left well and nudge back for the center well and nudge right for the right well, basically. And any torque and drag person knows where you have high tensile loads, which is up shallow, especially when you're horizontal, that's where you get a lot of different, that's where you're going to get higher torque. And higher torque is more problems drilling. Okay, high torque means less energy at the bit, drilling hole, and more energy trying to destroy your iron in the hole. Is basically what it means. And of course, when you're drilling this shallow nudge, which is really like a 5 to 10 to 15 degree S-shaped well, basically, and where you go back vertical, it's easy peasy to do that, because there's no real loads in there, and you can and it's even easier with a rotary steerable system, but you can put these S-shaped wells in there. And sometimes they bite you, sometimes they don't. This is why you do torque and drag analysis. I've been doing that for 30 years or so, and I don't want to second guess what's going to happen, because there's so many complications in the well. Is a certain direction of an S-shaped well going to cause problems when we're out in the lateral? Will it cause more problems when we're actually in the landing? You can make a case for a bunch of dog legs in the back build causing problems right when you land the well and adding to a big hump or a spike right in the heel, which is really bad for the well. Now, the solution, which has been around, is to not do S-shaped wells. I mean, S-shaped wells are the bad thing in torque and drag analysis. And if we want to go back to that previous iteration I was talking about, like extended reach wells, putting a dog leg in the shallow section is truly a no-no. I mean, I have asked directional drillers to be excused from projects for doing that thing in the different projects that I have run. So that's bad. Now, it's interestingly enough, like what they do in the Marcellus, they do what's called a 3-dimensional slant. Instead of getting out to some location with an S-shaped well, they'll take off in a direction kind of like landing in Hong Kong, if you've ever been there and you got to navigate around the mountains. They shoot off in one direction and arc around and come into the landing, with a 3-dimensional slant plan. I mean, these are still really small wells. They're, less than 10 degrees per 100 foot, but you have to control inclination and azimuth, and it's a more complex plan to do, but it's a heck of a lot better in terms of torque and drag and drilling mechanics. The planning softwares have been able to do this for 20 years. It means you have to watch tool face. Again, and actually a 3-dimensional slant profile is easier to do with a motor than an S-shaped well is to do. And they're all fairly easy with a rotary steerable.
Yeah.
I mean, I'd almost make a case for, if you have substantial nudges and you're having problems with them, do a rotary steerable.
I feel bad because for a short period of my career, I was a well planner. And
Yeah.
they're like, we need to be able to get out over here. And I was like, oh, we'll just put the little nudge in here at the top and then we'll get back to being vertical. And looking back at all the wells I planned that way, I was like, that was like the worst thing I could have recommended. But then again, I was under the leadership of other people, and they'd been in the industry longer, and so they approved it. So.
I bet you could get casing to bottom.
Casing still at the bottom. So David Reed, who's the Chief Marketing Officer at NOV, is watching. So David, thanks for watching. Previous guest here on the show. So he asked about, he actually said, what about the ability to complete? Doesn't tortuosity make it a challenge to consistently get completions in the well? He says, if answered already, then never mind. So, never mind. We've kind of already answered it, but I'll let you... No, I won't. I got to go to the next one.
Yeah, okay.
Because if not, we won't get through all of them. So we've got one more here. So we've got Jordan Timms is watching. Jordan, thanks for watching. Rithi had already said, thank you for answering his question. He appreciated that, and so did Kazim. So Jordan's question, just tuned in, sorry. Is Bill able to address coil tubing drilling's buckling limitations in laterals? Drilling new hole, not re-entry. I will add to this as well, because there's some guys that I know that are on the through tubing applications who are complaining of if they have a twist off or a thread failure, that they are the ones that they have to pay for the fishing, right? The service company has to pay for it, and what they're saying is that it's because of the tortuosity and the bending loads and stuff that they're getting inside of through tubing. So as the question goes there, then is there a way to be able to correlate the driller's wellbore tortuosity through to the through tubing applications as well? Could we, on drilling, be causing problems for the through tubing drilling?
Well, sure.
Well?
This is all through torque and drag analysis, and any torch towards the end of the well, you can from a drilling point of view, you can put a lot of tortuosity in it, but and I think the people that do torque and drag analysis know the cardinal rule of the second form of side force, which is that side force is caused by a tensile load across the bend. So where do you have the largest tensile loads? Up shallow, and you have a neutral point somewhere down there that's close to the bit, and below the neutral point you have weight on bit. Okay, the rest of the string is in tension, so where you have the biggest tension, and if you have dog legs or tortuosity there, that's the tortuosity that's going to cause you trouble. Well, notice I said tensile load, really. Whether it's tension or compression, it works the same basically. And in coiled tubing, you're usually dealing with everything being in compression. You're trying to ram the coiled tubing down there. And okay, you got a vertical section, but if you're going out at high angle, if you're going out above the angle of repose, which is about 75 degrees, where it costs you more tension to get down, then you're going to eat up your tension budget faster if you have dog legs there. So and again, it's a narcotic. Drilling fast up shallow, you can do it and get away with it. The problem doesn't manifest itself until you're trying to push that coil out there, or you're trying to push whatever out there. Now with drill pipe and casing, we can rotate, so that problem has vanished from us. But the coil tubing people still have to do it. What they ought to be doing is, as they're drilling the well, they ought to almost be running a real-time torque and drag analysis that goes from this idealized plan that you used to make that didn't have any curvature in there. Well, as you drill it, add curvature to it. Add the dog legs that are shallow, And at the same time, just, okay, what happens when I'm pushing this coil in at TD? You know, in the idealized plan, I can push it in there, and you're going to have some sort of tension at the surface. But you can actually calculate what your side force and tensile profile is for the cable as the coil as you're drilling, and you can actually see what this dogleg is going to cost you, or this S-shaped well is going to cost you. If there's a nudge in a lateral or something like that, especially if there's going to be coiled tubing operations, which you really ought to budget for. How much more do you get by going to one of these slant 3D Js, if you will, versus an S-shaped nudge? I mean, it'll be an astounding difference. So if coil is going to be an issue, and coil is much more susceptible to tortuosity problems than, as the aforementioned drilling and casing, which we flogged to death. You can get the casing to bottom. If coil is going to be an issue, then you really should be paying attention to what's going on, both in the design of the nudge and in the tortuosity introduced into the nudge. And that probably even to an extent into the build too. But really the shallow is what's going to hit you hard.
All right, guys. Well, we've wrapped up all the questions that have come in offline. If you guys have any more questions, you need to fire them off quick. We're not keeping you, are we?
No, I'm fine.
Okay,
I'm fine,
okay.
yeah.
So let us know. Hey, guys, let us know where you're watching from. Please feel free to share this video. Let other people gain in the same knowledge that you're gaining in as well. We really appreciate it, as well as if anybody wants to click one of the little buttons at the bottom just to let we know that people are watching. Like, there's no metric based off of this. It doesn't, do anything for us. It just allows us to be able to know that people are actually watching.
Did you get his question?
Yeah, that one just came up here.
Okay.
All right, so Rithi has another question. Does Bill have any recommendations on who or what training to pursue for good torque and drag modeling?
Wow. Okay. As I like to say, there are three flavors of torque and drag packages. There's the one that costs $1,000. There's the one that costs $10,000, and there's the one that costs $100,000.
Did not know those numbers.
Yeah, right. And I get this question asked in my consultancy. We need to do torque and drag analysis. We don't have a package. What do you recommend? A lot of times they pick the $1,000 one. And guess what? It uses a lot of spreadsheets, and it's not as easy to use and whatnot, but it is quite good. Training, let's see, I haven't done that in so long, but go online, look at different people that do torque and drag packages. I mean, K&M, the people that are teaching torque and drag are the extended reach people. Like K&M, which, of course, is wholly owned by Schlumberger, which I used to work for. But I have found that the various vendors that sell torque and drag packages are relatively good at helping you out with those things. Now, you're not going to get much for $1,000, but you get a package that if you're starting from scratch, it's really hard. Probably PetroSkills or some of the other places, they have the basics of these things. I mean, I taught torque and drag for 10 years. Enjoyed doing it because so many people had so many misconceptions about it.
I'll just put your phone number out there.
Yeah, I mean, find somebody better than me that can do it. I mean, if you're really starting from scratch and you really have a bad problem, yeah, I could help you out with that. But the best thing is to go online and look at the people that are selling different torque and drag packages, and because you're gonna.
Or have them go do that research, and then they could vet it back through you and say.
Well, that's exactly what I do. I mean, when it's been a year or two before somebody's asked me about it, I just go online and look and see what I can see. That's really the best way to do that. Send me an email. WGLessoJR@gmail is me. I'll send you some names and I'll tell you who's 1, 10, and 100 if you want. I don't want to talk about that here because then we'll really catch all kinds of hell. But you know what I mean. And it's out there. It depends upon where you are and how tough your problem is.
Yeah, I just want to say, Tyler watching from Southwest Energy's office there. Tell Sean and Denari that we said hello. It's some of the guys, their remote ops center. So I said thanks, David and Bill, watching from Houston. So thanks, appreciate it. Let's see. I'm curious about tortuosity concerns and AC concerns in the upper hole section for larger well pads, like in the DJ. This is a well planner from Coltech Energy Service, Kevin Wong. Kevin, thanks for watching. Appreciate the question.
That's an area we haven't touched on. I've talked about really environmental placement issues. I haven't talked about anti-collision and ellipsoid of uncertainty calculations, which is a whole big part of this.
I was about to say, let's not go down that rabbit hole. That one we like.
But
I still have to eat lunch at some point.
Oh yeah,
I know we can get, because that's one that
that's a different subject, and I would almost argue that anti-collision issues are even bigger than this. And they certainly are, like they're saying in the shallow hole section, where you have all these, you line up all the wells.
And anti-collision is going to supersede any wellbore tortuosity issue as well. So like you need to, I would say you take that one into consideration first. They're like, oh, we have to put a kink in the well here, but it's to keep from hitting and knowing that we're not going to hit a well over here. Then yes, that needs to take place.
You have to do that.
You have to do it. But then after that, it's like, okay, or at least in the execution of doing that, there's probably better ways to be able to plan it out. Okay, if we need to do this an S well up high, or could we potentially do this a little bit smoother? So
yeah.
I've learned from my bad well planning mistakes, so I'll say that as far as.
And you should have been able to plan that well without having to put a kink in there. Now, if something happened, but yeah, to frame this, the accuracy and anti-collision and EOU issues supersede down tortuosity. I'm talking about, down in the lateral where it's not as much of an issue. But certainly, if I'm talking about all these wells around and I'm talking about wobbling left and right, if you don't know where the well is, if you haven't reduced your survey accuracy placement considerations, then you shouldn't even be playing this other game. You are down the wrong rabbit hole to start with. So, and what I've seen, and if you look at the surveys, and you and I look at a lot of wells, they have all kinds of surveys in the S and the shallow nudge, usually gyros on a 25-foot spacing, which is great. So I'm seeing that people truly are addressing the survey accuracy, AC, EOU type of issues, and that's why what we're talking about here is after you've done all of that, and now you're down in the build to horizontal and in the actual lateral, and what we ought to be looking at there.
So what advice would you give to a directional or service provider to be able to frame this conversation, to be able to go back to an operator and legitimately be able to get maybe some traction with them? When they, should they go in and they say, hey, look, we've got the torque and drag modeling, we've got better low bend angle motors, whatever that conversation, whatever they need to do on their side to where they can then go over to the, to the operator and say, hey, look, please let us help you. Because obviously from the operator side of it, they've got so much going on, unless it's Rithi or some of these other guys that are tuning in right now, who are actively trying to do this. But like from a service company side, what do you see there that they should really latch on to?
Well, I think that completion ought to be represented in the well construction process. What are your completion engineers saying about the lateral that us directional drillers are delivering to you? Are they happy with it? Do they have any concerns about designing their fractures, you know, and you know, where are you on setting the casing? You know, are you having casing failures? Are you using premium connections when you really don't think you should be using them? What kind, you know, how I mean, I don't know where the operator is on who's responsible for the integrity of the casing, but that's certainly a starting point. You know, do you feel you got good integrity, you know, a good cement job? Not that they're going to run a bond log or anything like that, because I don't think anybody does, but maybe they do, maybe somebody does. But you know, if a directional drilling company, and a lot of them do, I mean, I have found that people routinely do less than 1 degree per 100-foot tortuosity in the lateral on a lot of their wells. You know, I've made this list of the operators, and I find that tortuosity correlates by operator. So it's the drilling practice of the operator. You know, you're in the green zone if you're less than 1.6, you're in the yellow zone if you're 1.6 to 2, and you're in the red zone if you're above 2, basically.
And I want to comment on that, because I remember seeing your report on that, and that the wellbore tortuosity lined up more so to the operator than it did to the service company.
I found it correlated to operator.
So so for anybody who's challenging it, he's already looked at that there is a correlation there to the operator side of it, not so much to the service company side of it. So it is kind of that leadership top-down mentality. So there's an ability. So I always kind of look at this, because I think of, for the service companies, there's an opportunity there to, one, differentiate yourself in a very highly competitive market, and to be able to say, hey, look, let's go in here and look at our operators' goals as a whole, and if we can be the leader in that, we can be, you know, the one that brings up that tough conversation, then there's possibly or potentially the ability there to be able to gain even more work in the future, because we were the ones who spearheaded that problem. So it sounds like some of these directional drilling and service company providers should be trying to go to maybe some of the completions events, not maybe going to all the IADD events, even though please do attend all of the IADD events. Going to some of these completions events. Maybe we need to have an IADD and completions event like together or something, and be able to talk to those completions guys about what are the issues that they're facing, and then us listen to those problems and see if there's something that we can figure out. You know, maybe there's a common link there. I know that even with Jonathan Lightfoot said that, you know, the Oxy drilling side has, you know, the completions departments in there with them. Like, it's no longer two different silos. It's one and the same.
Yeah, and I mean, like the kind of example I would finish with is, you know, there's this company called Anadarko, which is in the red zone. And then there was this other company called Chevron that was in the yellow zone. And then there's this third company called Oxy, which is in the green zone. And Oxy made the case that they drilled higher quality wells. Now, they weren't using my tortuosity index or anything like that, but they...
But I mean, to their credit, like Jonathan Lightfoot, he is definitely one of the guys that spearheads a lot of wellbore tortuosity stuff, gets the conversations going.
He's the chairman of the ISQA.
Yes, okay. He's chairman of ISCWSA.
An operator has a person that is looking at tortuosity, and they bring their completion people in, and they have 1.4, 1.3, 1.4 tortuosity in Texas. And in New Mexico, which is where they say they're strong, their tortuosity is like less than 1. They drill beautiful wells, and I'm not involved in them. I'm looking at them at the public data. So you see an operator that is actually in their drilling practice. You know, I mean, like I say, they're looking at tortuosity, but I'm not involved in it really. I'm just an observer as to what they've done, and you know, and how it's going to wash out, but they convinced Anadarko to go with them as opposed to Chevron. I mean, and they
there might have
claim
been
to be
some
doing
dollars
better.
that went into that thing as well.
Money talks, and you know what. But anyway, and I do know that that in their construction process they bring their completion engineers. Now, are completion engineers suffering in silence with high tortuosity in some of these companies? I don't know.
Suffering in silence. There's a room full of completions engineers that
I
are
picture
all crying right
these
now.
guys are stoics, I mean, wow, this well only has, we only have 2.5 degrees per 100 foot of tortuous. They're not going to talk in those terms, but this well.
We only had better. 10 twist offs.
Yeah, right, exactly. So that but it is, it is the wider. I mean, we used to drill a well and complete it and produce it. Now these unconventionals, we drill them and we complete them, and then we have this major economic thing called a frac, which actually costs more than everything else in the thing. Yeah. And what we do, what us drillers do, the drilling and geologists do in placing that well, heavily, impacts this thing. And I mean, we're almost like the tail wagging the dog, because economically that frac costs way more than our little drilling part of it. I mean, I
always give people the example is that drilling is the part of the construction crew. Like say you're building a highway.
Yeah.
Drilling's like the guys who take down the trees and come in with the bulldozers and whatnot and just like clear out the landscape. And then completions has to come in there and deal with whatever we've, they're the ones that come in and actually
they do with concrete.
They're laying concrete and stuff and then production's the toll booth, And so I always say, it's like, okay, what are we turning over? Are we turning over like flat, like level grade land, or are we leaving them like tree stumps and stuff that are still like, where the road is supposed to be? So it's like, what are you turning? Because whatever we do on the very beginning part is what everybody else has to deal with going down the road.
The whole life of the well concept, and I mean, like I say, if we're saving a day and $100,000 or whatever a day currently is, and we're putting in all sorts of
you save you save one department a day, but you cost all the other departments 10.
Yeah, so that's what it is. It is, I mean, there's so much post drilling instead of just setting casing and perforating it and producing the well. There's so much going on that group of expertise has to be represented in what we're doing in the drilling process. And more operators are realizing that, and directional drilling companies who have all the skill sets to do everything I've talked about here, between tortuosity, different trajectory profiles, three-dimensional slants versus S-shaped wells, automated directional drilling. You could do this with rotary steerables versus motors, different bend housing motors, multi-well collision from the surface, looking at different wells and navigating in the horizontal. The directional drilling companies all know how to do this. The relationships with torque and drag analysis, running torque and drag analysis on drilling profiles, running them on casing profiles, and the whole skill set is there. We have tools that the completion engineers should at least know that we have available. And they now, if they think everything is fine, then everything is fine. But I would venture to say that everything is not fine, and we could help the completion engineers quantify, what they need to do to, again, make the biggest and the baddest and the best fractures bang for buck and get the best production out of it.
Yeah.
Fini.
All right, guys. Well, we'll end it on that one because I mean, there's no better way to end it. I will say this: Lee Smith said, "Great stuff, David and Bill. So refreshing to see technical-based industry content as opposed to surface-level leadership fluff." So, Lee, thank you for watching. I really do appreciate it. We're going to continue conversations like this in the future. If you guys, if you're trying to get in touch with Bill, Bill, what's the best way to get in touch with you?
Email WGLESSOJR @gmail.
At gmail.com.
Yeah, gmail.com. So is there another one? Anyway, just send me an email. I hope not either. And
Bill frequently attends the IDD events. You did a presentation one back in.
Oh, it's been a while since.
Was that one in April? I think it was.
Man.
I think we did it was drilling towards automation.
Yes,
the event.
That's right.
So that was April 4th. So if you're looking for any of the presentations or content that he's put out there is some stuff on the IADD website. So be sure to go and check that out. As always, you're also on LinkedIn, so they can find you on LinkedIn. Be sure to link up with him, connect, follow the stuff that he's putting out there. Thanks for everybody that's watching. Mark Anderson just said thanks. Mark, thanks for coming back to the show and watching us. We'll definitely have to do this again as we continue to progress. We should do this in maybe 6 months or a year and see how much further along the industry's gotten.
Yeah, things are changing right now. I mean, the implications of automating directional drilling, which is what came out in those April meetings that we were talking about, and what happens with tortuosity when you go towards automation is a very interesting subject.
I can guarantee you this, Mark Anderson would for sure want to be able to get in on that. Mark Anderson, John DeWart, probably David Reed as well. He's in that the DSAT group, the SPE DSAT group. So guys, thank you so much for watching. We really do appreciate it. Hopefully, if you guys have any more questions or whatnot, please feel free to send them across. I'll get them funneled over to Bill, or you can contact Bill directly. And as always, know your industry.